Today, let's look at transformations and point and line symmetry. First off, the term preimage. This is a figure before a transformation. For example, this blue triangle. The image then must be the same figure after a transformation. So if we take this blue triangle and move it, that's a type of transformation. The map is going to be the rules on how a preimage is transformed. So for example, if we describe the transformation from the blue triangle to the orange triangle, we can say that it was translated right 6, described as x plus 6, y plus 0. We'll talk about how you can write that yourself in just a moment. As far as types of transformations goes, the one that we just saw is called a translation. To translate a figure up or down, left or right, without changing its orientation or the way that it's facing. The slang term we will use is to slide the figure. So for example, we take this blue triangle, A, B, C, and slide it to be a new triangle, A prime, B prime, C prime. We can then count how far away it went. So for example, the bottommost right vertex moved 1, 2, 3, 4, 5, 6 spaces to the right, and 1, 2, 3 spaces up. So I can describe the translation as x plus 6 and y plus 3. A reflection is to reflect a figure across a line, creating a mirror image of the preimage. The slang term we will use is flipping the figure. So now we're going to see a mirror image of this right triangle across the line. If you imagined folding your paper in half across this line, you would be performing a reflection. In order to do this yourself, you might find it useful to actually think of it as right triangles. So you want to count how far down it takes from any vertex on the blue triangle and count the same over to the orange triangle. So for example, I can see the blue triangle is 1, 2, 3, 4, 5 away from the line of reflection. So the orange triangle must be 1, 2, 3, 4, 5 away from that line. This will be useful when you're doing it yourself. And we're going to describe this as reflected across the line y equals x. Keep in mind we could use the x-axis, the y-axis, or really any line. Rotation. To rotate a figure around a point of rotation. The slang term will be spinning the figure. So we're going to take this blue triangle and we're going to spin it. We're going to rotate it 90 degrees. If you imagine a little right triangle from the origin to one of the vertices, that right triangle gets rotated into the next quadrant. We're going to say this was rotated 90 degrees clockwise because it traveled to the right. If it traveled down, we would call it counterclockwise. The last type of transformation you might see is called a dilation. A dilation is to multiply the side lengths of a figure by a scale factor to create a similar image. You might hear us call it stretching or shrinking the figure. So for example, if you're given a preimage A, and we want to dilate A by a factor of 3/2. Well, first we're going to think about the vertices of A. And we're going to take each of those vertices, each of those xy ordered pairs, and we're going to multiply both the x and the y value by 3/2. So 0, negative 2, when dilated by 3/2, would be located at 0, negative 3. For our x values, 0 times 3/2 is 0, and for our y values, negative 2 times 3/2 is negative 3. So we're going to see that A is going to be stretched into A prime. Notice that the image is always going to be denoted by that little prime next to the letters. All right, now let's look at our types of symmetry. First, we have line symmetry. We saw this in reflection. This is the line of symmetry by which the figure is reflected so that the image matches up with the preimage. Bear with me. So if we ever have a line and one half of the line is identical to the other side, if you folded it in half, they would match up exactly. This is a line of symmetry. As you can see in this figure, there are several lines of symmetry. Another type of symmetry you're going to see is point symmetry. This is a figure which matches the preimage when it's rotated exactly 180 degrees. So for example, with this letter H, if we take it right side up and we rotate it 180 degrees, we see that it's identical. Same with this playing card, the Queen of Spades. When it's right side up And when it's upside down, identical. This is point symmetry. Here's some examples of our transformations and symmetry problems. So on the left, we see triangle A prime, B prime, C prime, and our original triangle ABC. Well, I know that the triangle on the left is my original, and the triangle on the right is my new triangle because of the prime symbols on the right. So here's the patterns we need to look out for. When they say the word translation, they really mean that something slid into place. I can imagine just picking it up, moving it to the right, and placing it down. When we hear rotation, we think about how it would have to spin to get into the new place. With reflection, we're going to think about it flipping across a line. In H, the line would be the y-axis, and in J, it would be the x-axis. So let's look at our triangle ABC. I see that for my original pre-image, to become my image A prime, B prime, C prime, I simply have to slide to the right, where A matches up with A prime, B matches up with B prime, and C matches up with C prime. This leads me to believe that instead of a reflection across the y-axis, it needs to be a slide across the y-axis. Notice that if A prime and B prime were switched, this might be a reflection. Now we see a pre-image A, B, C, D, E, and its image A prime, B prime, C prime, D prime, E prime, and we want to know what happened. Is it a translation across the x-axis? Did it merely slide into place? Is it a 180-degree clockwise rotation about the origin? Is it a reflection across the y-axis, or is it a reflection across the x-axis? So we're looking for that slide, that spin, or that flipping. So when I imagine these two becoming each other, it's not quite a slide. If it slid, it would have matched into place perfectly. Right? So let's imagine that rotation. So if it rotated 90 degrees clockwise and then 180 degrees clockwise, I see that it would look somewhat similar, but it'd be in a different quadrant. So it's definitely not that rotation. So if we look at a reflection across the y-axis or across the x-axis, I see it's definitely going across that x-axis. It's a reflection. So now a new problem. Which of the following is a dilation of triangle ABC with center of dilation 0, 0? Boy, that sounds intimidating, but don't worry, this problem is actually one of the nice ones. So when we think dilation, we're looking for a scale factor. So really, in the picture, we're given A, B, C, where A is at -5, 4, B is at 8, 6, and C is at 4, -5. We will now see if there's a common scale factor in each of the multiple choice options. So my idea is if I take a new set of ordered pairs and divide them by the old set of ordered pairs, I really want to find a common factor. Okay, so let's get started. X divided by x, -2.5 divided by -5 will be +1/2. Now the y values, 2 divided by 4 would be +1/2. So far so good, we have these matching scale factors. Well now let's look at b prime and b. So if we take 8 divided by 8, we find a scale factor of 1, which certainly does not match. So let's look at our next pairs. So looking at b, I see that a prime is -5/3, 4/3, b prime is 8/3 2, and c prime is 4/3 -5/3. So in the same way, we can take x divided by x. So we're going to take -5/3 divided by -5, which is +1/3. You could check my math if you don't trust me. Then for the y values of a and a prime 4/3 divided by 4 would be +1/3. All right, now let's whoa, I'm so sorry. Now let's look at b prime and b. So if I take +8/3 divided by +8, I find the scale factor is 1/3. If I look at 2 divided by 6, my scale factor is 1/3. And in my c prime divided by c, So my new figure divided by my old figure, 4/3 divided by 4 is 1/3, and -5/3 divided by -5 is 1/3. So because all of these scale factors are constant, I can see that the answer to the question is B. Now, for the following images, we will determine whether the image has point symmetry, line symmetry, both point and line symmetry, or no symmetry whatsoever. So remember, when we're talking point symmetry, we want to imagine it getting turned upside down. And with line symmetry, we want to imagine actually drawing a line through it. So on the arrow on the left, I can see that there's a line where if I folded it across the line, it would be identical. It definitely has line symmetry. But when I flip it upside down, it's not exactly the same. So it has no point symmetry. For my next figure, that doesn't work. I see if I folded this, the chips would be in different corners. So there's no line symmetry. However, if I flip it upside down, perfect match. I can see that it does have point symmetry. Now for the last big boy. I'm thinking it has no line symmetry. There's nowhere that I could draw a line where if I folded it, both sides would be the same. And if I flip it upside down, it's definitely different. So this figure would be described as having no symmetry.